what are the three different scenarios that you can end up with when you have two equations in a plane? So what we saw in that last example, we had two lines intersecting at a single point. Thus, there is exactly one solution. This is only one of the things that can happen when we have two lines in a plane. See if you can think of the other two things that can happen. Go ahead and pause it. I'm not going to wait for you. Okay, so one of the other things that can happen is, well, if you have the lines intersecting at a single point, well, what happens if the lines don't intersect at all? In this situation, points that satisfy the first equation are up here, points that satisfy the second one are down here. There are no points that satisfy both equations, thus we would say that there are no solutions. And I wonder, this third possibility is a little bit harder to think of because most people kind of rule it out, but what we have here is overlapping lines. So everything that satisfies the first equation is on here. Everything that satisfies the second equation is also on there. So that means that's a solution to both equations, thus a solution to the system. That is a solution to both equations. That is, there are infinitely many solutions. These are the three different scenarios that you can end up in when you have two lines in a plane. Either they completely overlap, they don't have anything overlapping, or they intersect in exactly one point. So when we have a system of equations that results in each of these, we have some vocabulary that you just kind of need to have written down or memorized or whatever. I'm just going to cover that now because it does show up in your homework. So when you have solutions, at least one solution, we say the system is consistent. So that would be in this case, the system is consistent. And similarly over here. Because there are infinitely many solutions, there's at least one there. In this case where we don't have any solutions, we would say the system is inconsistent. Alright, so like I said, this is just some vocabulary, some ways of classifying that are sometimes talked about. An inconsistent system is when we have the two parallel lines or when there are no solutions. When we say the system is consistent, though, we don't know which of these two situations we're in. We don't know if there's exactly one solution or infinitely many solutions. So we need to get a little bit more specific. Over here, we would say the equations are independent. Versus over here, the equations are dependent. Yeah, this notion of dependence we're not really going to cover in this class. If you get further into linear algebra, dependence actually means something, but whatever. We don't need to know that. We just need to kind of have memorized that vocabulary. We don't need to know anything more than that. How do these scenarios work in 3 dimensions or 4? Alright, so this is where it becomes a little bit more tricky to draw on a surface and describe what's going on. But imagine in the room you're in, or, well, maybe not the room you're in, maybe you're outside, who knows. Imagine you're sitting in a classroom. I'm usually doing this in a classroom. We have the room has walls. And let's focus in particular on these walls are essentially planes. They're flat surfaces that go on forever. Or, well, we're going to pretend they go on forever, Of course, the actual walls don't, but the plane that this wall exists in would go on forever. This wall, maybe this is where the whiteboard is, and, I'm standing up here pointing at things on the wall. There's that wall, and that wall intersects this side wall all along this corner here. So if you're talking about two planes in a 3-dimensional space, you can see we can't really get it down to just a single solution. Even if you were to move these around, think about two planes intersecting. Maybe we're talking about this front wall and the floor. Well, in that case, this whole line is are points that are in common between those. So those would be kind of considered solutions if we're talking about the two of those. However, if we, instead of having just two planes in the three-dimensional space, if we considered having three planes in this three-dimensional space, so not only this front wall and the side wall, but also the floor, if we talk about all the points that are in common between these three planes, you can see this point right here would end up being the only point that's in common. So when we're talking about in 3D, three planes can, we can get a single point here, can have only one point in common. This would be the situation similar to what we had up here, where we had the system being consistent. So if we have three planes, namely the front wall, the side wall, and the floor, then we could get those three planes intersecting in a single point. And we could have, this would end up being three equations. Each of these planes is its own equation. That's kind of how it ends up working in 3 dimensions. Those equations give you planes. So what about these other scenarios? How about, can you think of, going back to my classroom scenario, can you think of three planes in this room that I've kind of set up there where you might have no solutions? Or maybe is it even possible to do it with just two planes in that room? Well, let's see, I'm here up at the front of the room. Let's not use that one for the moment, though. There is a side wall over here, and there's a side wall over here. If we consider these two planes, this plane and this plane over here, you'll notice there are no points in common between them. This would be no solutions here. So we can end up with, maybe we're taking these three planes even, but there would still be no points in common between all three of these, because even pairwise you don't have any points in common between just those two. So this would be one solution. And can we think of, we're going to have to get a little bit out of the thinking of our classroom scenario here, but let's again focus on these two walls. Let's try to decide, is there a way that we could have a third plane in here where we might still have infinitely many solutions? I'm trying to match up to this kind of scenario up here. And well, if I had another plane, it's not going to be an existing, a wall or anything that's part of this room, but let's imagine a plane that goes through this line. So let's say it kind of cuts through the middle of the room here. That plane right there, or if you take these three planes together, they would have this entire line in common. And this is one way to get infinitely many solutions. Oops. Let's go draw the little infinity sign. Infinitely many solutions. So it certainly is possible to get the kind of the same sorts of flavors of scenarios when we're talking about two dimensions. That's what happens when we're in a plane. We have kind of width and height. That's 2 dimensions. And generally we talk about two equations in 2 dimensions. When we're dealing with 3 dimensions, in other words, 3 variables, that's another way of saying the number of dimensions in general. If we have an x and a y, this is 2D. If we have in 3D, we're going to have generally an x, a y, and a z. Those are the 3 dimensions we tend to use, the 3 variables we tend to use to represent our dimensions, rather. But it's entirely possible to still have these 3 same scenarios. We could have one solution, exactly one solution. We could have no solutions because maybe something just doesn't work there. Or we might have infinitely many solutions. These are certainly not the only ways that these could happen. These are just some examples of one way they could.